Today's lesson is on logarithmic functions. Before we get into logarithmic functions, we're first going to start off with a function that we already know, an exponential function. In this case, f of x equals 2 to the x. And what I'd like you to do is find the inverse using the skills we learned in the inverse functions section to find the exponential function's inverse. So, just going over the steps, my first step was to take f of x and replace it with y. The next step said that now that I have a y in my function, I'm going to take the x's and the y's and interchange all of the x's and y's, and that's the inverse step. Once I have the x's and y's interchanged, then I solve for y, and finally I replace y back with f inverse of x. Alright, let's try this function, f of x equals 2 to the x. My first step says take f of x out and replace it with y. So I have y equals 2 to the x. The second step says take my x and my y and interchange them. So I have x equals 2 to the y. Step 3 says to solve for y. So I need to get the y all by itself on one side of the equation. Now, my y that I'm trying to solve for is up here. And actually at this point of our learning, we actually don't know how to get the y, the variable, out of the exponent like that. I don't know how to solve for y, so I'm kind of stuck. I got to this point and we cannot actually find the inverse of the exponential function because we have not yet learned to solve for the y in the exponent. So this is presenting a problem. I can't find the inverse of an exponential function because I can't get the y out of the exponent. So what we need is a new notation for the inverse of an exponential. So I want you to understand that although we cannot solve this now, we will come back to this problem later in this section. But for now, we need to take a little deviation and just learn that new notation before we can actually come back and find the inverse that we were looking for. So I want to liken the inverses to some inverses you've seen in the past. If we're talking about addition, we know that subtraction is the opposite of addition. And we use that like when we're solving, let's say x plus 3 equals 7. What are you going to do to both sides here? Well, I want to get x all by itself, and I need to get rid of the plus 3. I do the opposite. Opposite of plus 3 is minus 3. That's the opposite operation, and then I can get my answer. Now, I know you all know how to do that. The point isn't, can you solve this linear equation? The point is, we did the opposite. We know addition. We know subtraction is the opposite, it undoes it, or is the inverse. Also, we know that division is the opposite of multiplication. And we've used that in the past. Let's say 4x equals 12. What are you going to do to get x by itself to solve this equation? Well, the opposite of multiply by 4 is divide by 4. So when I divide both sides by 4, I'm getting x equals 3. And the reason I'm allowed to do that is because the opposite of multiplication is division. Going one step further, we have the opposite of a square is the square root. Square root is the opposite of square. So if I had an equation like x squared equals 9, and I'm trying to solve that, I know I can do the opposite of square, which is square root, to get x all by itself. So I have x equals plus or minus 3. So square and square root are opposites. Multiply and divide are opposites. Add and subtract are opposites. So similarly, we have exponential function has an opposite or an inverse. And this is called a logarithm. And we need to understand the notation of a logarithm. But I want you to know that this notation, although may seem a little cumbersome and long, plus and minus were foreign to you as well when you were much younger. My kindergartner, she knows what a plus is and she can identify a minus sign. And so you've been dealing with pluses and minuses for a really, really long time. And so they seem almost second nature to you because you've been adding and subtracting. A little bit later on in your education, you learned about multiply and divide. And now you can do multiply and divide really, really easy. But at some point of your education, the notation for multiply and the notation for divide was difficult for you. And maybe not too long in your past, the square root symbol, which was the opposite of square, was also introduced to you, and before you knew about square root, when the first time you saw square root, you were like, ah, it looks crazy, what is this little house thing? But eventually you come to use square root so naturally because we use it so often. That's the same thing with this logarithm notation. When I present it to you, students often get a little scared. They're like, oh, what is all these notations? I don't understand it. But it's just the opposite notation. It is a little bit cumbersome. It's not quite as simple as just a plus sign or a minus sign. But in time, you'll be able to use the log function just as easily as your add, subtract, multiply, divide, square, and square root. So let's talk about that logarithm function. Let's say I have an exponential function, b to the y equals x. I can rewrite b to the y equals x in another form, in a logarithmic form. This if and only if means if my first statement is true, then that means my second statement is true. Conversely, if my second statement is true, that means the first statement is true. That's what this if and only if means. So if b to the y equals x, if that's a true statement, then this must also be another true statement. Log, L-O-G, short for logarithm, base b of x equals y. The exponential equation, written b to the y equals x, and the logarithmic equation, log base b of x equals y, are equivalent. If you have one, then the other must be true. If you have the second, then the first must be true. There's a few things I want to note on this. Notice that my base is the same on both of them. Not only is it the same, we actually pronounce it exactly the same. When I pronounced the logarithmic equation, I said log base b is how I pronounced it with my words, of x equals y. That's how I pronounced log base b of x equals y, this expression or equation over here. So the b, which we call a base in the exponential, and the b base, which we call base, notice we call it the base, is the same in both. But one thing I want you to note is that the x and the y kind of switch sides, they change places here. Notice my y is the exponent of b, and x is the equals on the other side, and the x is now with b as the argument. The number or expression right after the log is called the argument of the log. So this argument and the y have also kind of switched sides. On the exponential, b and y are close to each other on the same side. On the log equation, b and x are close to each other. So the x and the y kind of switch sides. So when else have we tried switching the x and the y? Well, for the inverse, and that's, because they're inverses. So that's one way to remember this, is we switch the x and y. Well, why? Because log and exponential are inverses, and that's exactly what we're trying to learn here. And I'd like to say just one more time, I know that this log equation looks a little scary, but this is just notation that you're going to have to learn. Just like you learned addition and subtraction, multiplication, division, square and square root, the exponential equation and the logarithmic equation are inverses, and this is just a new notation. You have to write the log to represent the opposite or inverse of an exponential function. That's just the way whoever came up with this wrote it, and we have to then follow it. So that is how we write a logarithm function. Now, some bases are used frequently and have simplified notation. The first simplified notation is of the common log, and the common log always has base 10. So we have log base 10 of any argument, in this case we'll say x, can be rewritten as log x. Notice I didn't put a base here at all. If there is no base here, you need to assume that the base is 10. which is the system that we work in. We work in a base 10 system because we have 10 digits before you have to use 2 digits to become another number. Also because we have 10 fingers, this is why we probably use the base 10 system, and that's why base 10 is so common. Okay, think about it as your hands here. 10 fingers, very common, everybody has them, so that's your common log. Another base that is used an awful lot is base e. If we have a log base e of x, we really don't write it this way. No one writes log base e. This is the natural logarithm, which we said e was the most natural or preferred base to use when we're using exponentials and conversely logarithmic functions. And the way we write a natural log is ln. You don't put a base e here. The ln stands for natural logarithm, or logarithm natural. So we have natural logarithm of x is the same thing as log base e of x. Please don't write your answers log base e or log base 10. You want to write them in the preferred simplified notation. So just in a summary, if I have in the logarithmic form y equals log base b of x, the equivalent exponential form would be the same base b. The x and the y are going to kind of switch sides. So instead of the x being with the b, it's going to be the y with the b, and the y is going to be in your exponent. Therefore, the x has to be on the other side. On the next equation, y equals log x, there is a missing base here. Now, does that mean there isn't a base? No, it means there is a base. The base is an invisible base 10. You can write in base 10 while you're working your problems, but if you're answering your problem, make sure that you're leaving off the log, and that's just an invisible base 10. So I can rewrite this as my base 10 raised to the y. Notice the x and the y need to change sides. The base is with the x, so now the base needs to be with the y, equals x. Similarly, y equals ln x. ln has a base of e, so in exponential form we have e to the y equals x. This is just a little bit of summary of what we've been trying to talk about earlier. Before we move on, I want to make one more little comment here. Do you guys remember that paper from kindergarten with the big fat lines, and then you had this like dotted line here in the middle? I bring out this elementary school paper or kindergarten paper because I want to make sure that you're putting your bases and your exponents in the correct place, either sub below the line or super above the middle line. So if I have log base b, the log, the log part of it, is on the normal line. It's the same size as normal letters, and it's not high or low. But when I do b, I do my base b below the line of x equals y. And y could be on the other side if you really wanted it in the front or in the back. It doesn't really matter where you put the y. Its equivalent statement is base b. Notice the base b was small in the log equation, but in the exponential equation, base b is normal size. To the y, that means y is little n above, or superscript, equals x. So there's only two places where your letters are either small and above or small and below. And what's in the log equation, you have a small base b, all the other letters are the normal size. And on your exponential equation, you have a small exponent, in this case y, and that's above. All the rest of them are normal size. And you might think, well, why in the world is she telling me all this? And the reason is because on tests, I often see people kind of write a little messy. They kind of write upwards a little bit because they're not sure where the base b and the x is high or low, and so they kind of just write at an angle. Yeah, I know what you're doing. You don't know what the size is here, and so you just write a little bit messy and upwards, and that's not going to cut it. I really want to make sure that you know right in the beginning where the superscript is in exponential and where the subscript is in logarithmic form, and everything else is a normal size, so that even if you're watching someone else's handwriting, you still understand where to place your super and your subscripts.